Steve. Yes, so indeed it's some collaboration between UPenn and Seoul National University. And we're going to talk briefly about coinduction, but the talk can kind of be split into two distinct parts. First, we'll talk about coinductive reasoning in general, in the sense that we will propose a generalization of an approach that is called parameterized coinduction, and that is in particular implemented as a Paco library in the Coq proof assistant. And then we will see, inspired by this approach, we'll use it to implement something that is more domain-specific. When specifically you are reasoning about weak bisimulations, then we will see the approach that we propose to do so, that we call parameterized weak bisimulations. The exact relation won't be obvious during the presentation because it relies on technical details that we won't cover, but essentially think of the second one as using the first part for its implementation. All right, so let's start with GPaco. So in order to make things a bit concrete, we will work with this data type, so a very simple data type, which is finite or infinite list of naturals. And you can think of it as kind of like the trace, in a very simplified way, the trace of execution of a program. So you might have the empty list as your data type. You might first have some kind of silent internal step, so a step of computation you do not wish to observe. Or you may have observations. So here we'll just represent them as natural. So a K for a natural that is observed, and then the remaining of the stream. And we will use tau to write the silent step. And so, of course, we are concerned with the greatest fixed point of this functor, so nu for the greatest fixed point. And we won't really worry, actually, how we take the greatest fixed point as far as the data type is concerned. To make things concrete, such an element of the data type can be a finite list, 0 then 1. It might be the same finite list, but with some internal step on the way. It might be an infinite alternative streams of 0 and 2s, or the same with some internal steps. And then there is this very peculiar one, which is a silently diverging stream. So this is very standard. When you work with this kind of constructs, what you want really is not to worry about internal steps. You want to ignore them. So you want to identify the first stream and the second one, as well as the third one and the fourth one. So this is working with some notion of weak bisimulations. And the usual tricky part is you want to be a bit careful so that you don't start relating this silently divergent stream to everyone. We won't get into the detail of the functors that define this relation, but you have to have in mind that here, this functor is once again something that you want to take the greatest fixed point of. And as much as I didn't care about how I take the greatest fixed point to construct my data type, I should just specify that eutt stands for equivalent up to tau. That's just a notation. So as far as I didn't care about how I take my greatest fixed point for the data type, when it comes to defining the relationship, it actually matters because it will define what kind of reasoning principle I get. And so the idea is that if you do it as a Coq coinductive relation, you have this notion of guarded coinduction, basically the cofix keyword in Coq. And it's well known that as much as it's convenient to use, it allows you to build your proof incrementally. The problem is that what will validate a correct term is a syntactic criterion. It's well known that it breaks automation and composes poorly in some senses. If you forget about Coq for now, and you think just more of the lattice theoretic approaches that are well known in the domain, then the basic proof tool that you get is Tarski's fixed point theorem that basically tells you that any post-fixed point is included to your greatest fixed point. So it's like think really hard, think about your proof, come up with the right post-fixed point, and go through it. So this is inconvenient for the way you build your proof. It's not incremental, but it's a semantic guards that actually qualify whether it's valid or not. And that was basically kind of the landscape in 2013 when Guider and his co-author introduced the notion of parameterized coinduction, which essentially solved this situation in the context of Coq because it allows us to have a library, which is called Paco, that both has this notion of incremental reasoning that allows you to construct the proof interactively, but semantic guards that recover nice properties about these proofs. So just to make things concrete, what I would like to do is to take this example and both kind of try to explain you how Paco works and why it's a great approach, but also pinpoint a deficiency of the approach and how we fixed it. So the way you will read this example is basically to think of each of these automaton as a stream. So for instance, if you start from the state S0 here, it's a stream that will first emit a 0, a visible step, then do an internal step, emit a 1, emit a 2, and it loops. So it's an infinite stream. And to the right, you basically have the same stream, but there is no internal step among it. And what we propose ourselves is to prove that the stream that is defined by starting from S0 is weakly bisimilar to the one from T0, and the one from S1 is weakly bisimilar to T1. So just to emphasize why weren't we satisfied with the situation without Paco, is going to be a very caricatural take on it. But essentially, the intuition is, if you were to work with a coinductive relation in Coq, naively, you could start your proof, say, let's do a cofix. And if you were to do auto, then Coq say, you're done. That's fine. However, of course, if you try to close the proof, only then it will tell you that he has to reject the proof. Caricaturally, on the other side, if you take the Tarski approach, you kind of have to think about your world proof and say, here is the total list of all the pairs of states that we'll have to relay during my proof. And the point of Paco is to kind of nullify both of these problems by saying what we do is we work with this G of eutt-F, which is just a notation to say, I take the Paco of eutt-F, which is one way to define the greatest fixed point. The good point is that you can start with just the two pairs of interest that you are trying to prove are in your relation, and you will incrementally build the bisimulation that you would have to come up with upfront otherwise by using this parameter, which is a parameter that records essentially all the states that you encounter that you are using to build your bisimulation. So we have this parameter that is important. We start with no information, VMT, and we will see how we use it now to conduct a proof. So the way it works is that we start our proof, no information, and we have a rule accumulate. So it's a X, it's these two pair of initial state. I can record that I've encountered them. So far they are locked. They are behind the construct of Paco. Then we can unfold the definition, and it tells us, first you have this functor that you should apply, and if you go under the functor, then you get access to information. So we do step. So when we stepped, we match the 0 with the 0 and the 1 with the 1. So we get these two new pair of states. And now we have unlocked this information, this X that we have recorded. So we could conclude the proof. However, of course, we step to new states, so we are unable to conclude. So instead, we keep going. So we can record more information. Now I have recorded both X and Y. Now what I'm trying to convey as the deficiencies through this part only happens when we do the case analysis. We have two pair of states, red and blue. If you look at the right pair of states, everything goes smoothly. We basically say, we again step, we match the step that's emitter 2, and we get two new states that now happens to be in this Y information that we just accumulated, so we can conclude. However, in the other case, it's a bit different. What's happening is that here we have this tau step, and it's very easy to prove a lemma that going under one tau on a side is not going under the functor. However, you can just ignore this step. That's a side lemma that you can prove. And that would be kind of satisfying to be able to say, now I am back to S1 and T1, and these guys are in this information that I unlocked during my very first accumulation step. However, it turns out that I cannot access it anymore because the information is locked under the Paco construct once again. So this is kind of the first issue that we fixed in this paper, which is there was in some kind of sense, there was a leak of information in the Paco approach, and we fix it by having two parameters instead of one. Now we have this R parameter, so the G hat is this generalized Paco, which captures the information that have been released so far, and the guarded parameter is basically the previous parameter, the one that is still guarded under the Paco that you only get once you go under the functor. And the definition doesn't really matter here, but what is important is that you get this base rule that says you don't have to go under the functor and then access the information. You always have access to the released information. And it's important to understand that it's completely backward compatible in the sense you still define your relation itself through Paco, the old Paco definition, but you have new reasoning principle through an initialization rule that say, I want to prove my properties about my Paco relation. I can move to the generalized world. And reciprocally, you have the final rules that say any fact that you've established about the Paco definition, you can always use it, that it will always be included into the generalization. So this is the intuition. How does it work in practice on this proof? Well, if we come back, if we just follow the red arrows to focus a bit, we initialize, so we get our two parameters now. When we accumulate, we only accumulate in the guarded part of the relation, so that when we step, we actually transvase the knowledge in the guarded part to the released one, so that we accumulate again. This time, we do not forget that X has been released, so we can conclude immediately in the case where we were unhappy with. So to wrap up this part about GPaco, how do we sum it up? The idea is that there was a leak in the parameterized coinduction approach, a leak of information, so we fix it with this second parameter. There is another increment in what we did, which is that it's something completely orthogonal, but very important when you do coinductive reasoning, which is the notion of up-to reasoning. So So it has always been an orthogonal question and always compatible with Paco, but now we provide some native support for it. And the whole approach is backward compatible, so if you were used to use Paco, you can just use this and have new reasoning principle on top of it now. If you're interested in the details in the paper, but maybe more importantly, it's already on OPAM on the Paco release. So now we will switch to the second aspect, which is more specifically when I work with weak Bisimulation, how can I have nice reasoning principle about them? To sum up a bit like the core of our approach and the motivation for our approach, the question that we have is, assume that you are trying to prove that two streams are weakly bisimilar by using this G-Paco construct. However, you established before, through another proof, through a lemma, that you know that S is itself weakly bisimilar to S prime. The question is, can you simply do a rewriting up to this equation in your goal? Of course, in general, it's not sound. To see this, we can take this small example. We will assume that the rule is sound, and we're going to prove that the stream that just have an element 0 is weakly bisimilar to the one that just have an element 1, which of course is absurd. So how do we do that? Well, we start by initializing the proof. We work in this general world with two parameters, and then we'll say, let's accumulate. Let's record these two states. So of course, they are guarded. We can't access this information to conclude. However, since we can rewrite up to tau, we can add a tau in front of each of the stream so that we can now use these tau that we just added so that we can step under them, unlock the information, and conclude. So of course, this principle is unsound. However, it's really unsound because we are using a tau step when you step. If we are to use a this step, which is in a sense stronger with respect to the relation we're interested in, then it will be sound. So the point of our approach is to capture this intuition. And the way it works is to say, let's have a generalization of EUTT the same way we had a generalization of Paco. So the equivalence up to tau was a relation of stream. Let's define EUTT-G, generalized, that is parameterized by 4 notion of informations. So 4 is a bit much, but the intuition is fairly simple. Just to say you still have released information and guarded information, but you also have a distinction between whether it has been released by going under a tau step or released by going under this step. And we will exploit this distinction to recover a sound principle. So we won't go into the construction of this relation. We'll just see what are the reasoning principles that we get. So the main benefit, the payoff of this approach is to get this rule. So this rule was definitely not sound. However, now that we make the distinctions, we can do the rewriting S by S prime. But by changing the parameter that we get, we completely forgot about all the tau knowledge that has been unlocked. Instead, we recover only the beta knowledge, which is like a subset of the information that we got that is sound that we know that we cannot break by doing this kind of rewriting. So the whole point of the approach essentially is to get this rule. Now, it's a bit abstract if we don't know how this information flows. So let's just see at the other rules. You first have really the main soundness result, which is to say, once again, this generalization of EUTT is a proof intermediate. So you can always start the proof into this general world when you want to prove the usual weak Bisimulation. And you can invoke any lemma about weak Bisimulation to conclude your proof. Then how does it work with respect to information? You first have access to the information the same way you have access to it through G-Paco. So the release information is always accessible to conclude. And you can accumulate by essentially extending both of the guarded parameters. So far, it's completely symmetric in beta and in tau. It becomes asymmetric when you look, of course, at the proofs that are specific to the domain of application. So the step rules. So instead of having just I go under the functor, you have 2 step rules. One which say what happens when I step by matching beta, so silent step. Well, in this case, I only unlock some of the information, which is the guarded tau information is released, but the guarded beta information is not released. In contrast, if I go under a visible step, so I match 2 visible events that are corresponding, then what happens is that the guarded beta information is released to every parameter. And what is under the hood is that there is a very simple invariant of inclusion of these 4 parameters. So the idea is that tau is a subset of the information that gets released, and that is kind of unsafe, so you might lose it if you do a writing, but beta is some safe information that once it's unlocked, it will always be there. So just to conclude about this approach, the intuition is we take the same intuition about G-Paco that manipulates release unlocked information, and we can apply it to specific domains, so that in particular, we will have reasoning principles that differentiate which constructor has been taken to go under the functor. What I did not cover here is that we have more reasoning principles. In particular, there is an interesting notion of directed rewriting by weak Bisimulation. If you enforce that you rewrite your equation by having strictly less tau than before, then you can always rewrite without losing any information. And of course, the construction itself is of interest, but I will refer to the paper for it. Let me just wrap up the talk. So we saw, once again, GPaco. You might be interested in GPaco if you do any kind of coinductive reasoning in Coq. It's an extension of the Paco library that is available on OPAM and GitHub. Specifically for reasoning with weak Bisimulation, we propose a different approach. And for a bit of context, it should be noted that here I presented everything over streams, but whereas this project is born from the interaction trees project, which is a structure actually similar to the FreeSpec project that we saw this morning, which is more of a tree-like structure with potentially infinite and with silent steps. And it was to develop this meta-theory that we were interested in this kind of reasoning principle. And Leah will tell us about it on Friday if you're interested. Thank you.
Okay. Questions?
So if I understood well, so Paco essentially gave you a way to have a conduction principle. Did I understand correctly that what you're essentially doing here is a way to have a inductive conductive way of reasoning about the objects you're defining, like fairness assumptions, like having inductive steps mixed with conductive?
I do not think so. No, I don't think it has to do with being able to be inductive conductive. I mean, the functor itself that you consider happens to be inductive, but I think it's completely orthogonal. It's more a way to build incrementally your coinductive proof instead of coming up to build incrementally your Bisimulations instead of coming up with it upfront. And then the increment between the Paco and the GPaco one is to have a finer way to reason about the information that you accumulate, because it used to be imprecise. You used to lose information that was forcing you to duplicate some subpart of the proof. So it's improved on that. But maybe I just don't see it, but I don't think it has to do with inductive conductive reasoning. But maybe you have an intuition that I don't have on here.
What goes wrong if you try to get this incremental construction of the relation by just having a relation to start with that contains unification variables that you gradually fill in as you go, but otherwise use the baseline proof technique?
Oh, I actually have no idea. So you basically want to start with, to instantiate your Bisimulation as being the most general, but being like quantified over evals?
It's like the union of the points that you know are there and then some unknown other set, and you gradually fill in that other set as you go.
So I tried something like this in Isabel, and I was able to reproduce the examples from the Paco paper, because we have schematic variables in Isabel which are like that, so it seemed to work at least on the small scale.
Oh, interesting. Well, there is Gil that is actually the author on Paco.
Assume that you have this whole coinductive proof, but you want to specify some lemma describing half of the coinductive proof. It's impossible in Coq. You cannot state it. Like I proved lemma 1 and lemma 2, putting them together constitute a whole coinductive proof. You cannot state a lemma which is state half of the coinductive proof, but using Paco you can state it. You can prove it as a lemma.
So is there another question? I have one. All this is GPaco is implemented by doing a proof with respect to the traditional guard condition.
So Paco is a construction in Coq using basically re-implementing the lattices that you work on re-implementing the theory, and then GPaco is a construction that is itself defined in terms of Paco, on which you prove a meta theory.
But the Paco itself is built on top of the traditional guard condition.
Right, but it can take this approach that it completely wraps up the word approach into semantic words so that you don't, you never encounter any problem with syntactic words.
Okay. More questions? Okay, so we're going to
Thank you.